Imagine standing in a packed stadium. Everything operates normally until the event ends, thousands of people rush the restrooms at once, and the plumbing system completely chokes. In a pharmaceutical plant, a similar demand rush occurs every day, and if the pressure suddenly drops, it threatens millions of dollars of product. Purified water functions as a precision-engineered raw material, with a production cost that often exceeds that of the oil used in heavy manufacturing. If too many operators open their taps at the exact same time, the system pressure across the facility plunges. Without adequate pressure, the water stops flowing and becomes stagnant. Stagnation triggers a rapid domino effect. Still water provides the perfect environment for bacteria to form biofilm on the pipes, which then leads to immediate batch-ruining contamination. A system's reliability is measured by its physical capacity to withstand a sudden, concurrent demand spike without dropping below a critical hydraulic threshold. To defend against localized pressure drops, engineers employ a specific protocol, the peak load study. This is a rigorous, digitally monitored stress test executed on the physical equipment long before a facility clears for commercial production. The core objective is to empirically prove that the system's automated control loops can absorb extreme hydraulic duress without failing. To understand how engineers achieve this, we need to map out the hydraulic baseline, calculate the maximum facility demand, and finally run a simulated system crash. Building a sterile water network requires engineering an immediate automated mechanical reflex to set in pressure loss. The primary mechanical defense against biological contamination in any pipe is constant fluid velocity. Water moving too slowly creates laminar flow, where smooth, parallel layers allow bacterial clusters to adhere and multiply. To prevent this, engineers target turbulent flow. A strict velocity over 3 feet per second creates chaos that aggressively strips bacteria off the steel. This constant turbulence acts as a continuous physical scour, protecting miles of piping without relying entirely on chemical sanitization. Maintaining this exact turbulence is straightforward in a closed, isolated loop, but it becomes difficult when active taps are constantly bleeding pressure out of the system. Maintaining a strict minimum velocity across a highly porous, bleeding piping network is the central paradox of pharmaceutical fluid dynamics. Engineers solve this velocity paradox by mathematically predicting exactly when and where those demand spikes will hit. Designing a pump to maintain pressure even if 100% of the facility's taps open simultaneously is an inefficient use of resources. Instead, they rely on a specific metric called the diversity factor. The diversity factor is a statistical probability calculation modeling the absolute maximum number of user points active at once. In a network of 100 taps, the math isolates exactly 35 critical points. This calculated number becomes the precise parameter for the stress test. This statistical model bridges the gap between theoretical design and the unpredictable actions of human operators on the floor. The diversity factor provides a mathematical limit that prevents over-engineering while ensuring the system can handle its maximum designed usage. When that peak load hits, a specific set of hardware kicks in to maintain the baseline velocity. Looking at this control loop flowchart, at the center is the Programmable Logic Controller, or PLC, monitoring system pressure in real time. The instant an operator opens a tap, the system experiences a micro-drop in pressure, and the PLC detects this loss in milliseconds. It then communicates directly with the system's accelerator, the Variable Frequency Drive, or VFD. The PLC commands the VFD to instantaneously ramp up the pump's motor speed. This compensates for the lost pressure by pushing a larger volume of water into the network. The final component in this loop is the back pressure control valve, acting as the system's hydraulic traffic cop. This valve actively constricts. Instead of allowing water to take the easy exit out of the open tap, it forces fluid completely through the loop, ensuring distant rooms are not starved of pressure. A stable pharmaceutical water network relies on hundreds of these automated micro-adjustments happening every second, perfectly orchestrated by the PLC and VFDs. Ultimately, theory and hardware must be tested together on the physical facility floor. During the actual peak load study, engineers manually coordinate to simultaneously open the exact number of user points dictated by the diversity factor. The instant those valves open, the facility undergoes its maximum engineered hydraulic shock. Engineers monitor the PLC dashboard. This split screen illustrates the reaction. As system pressure dips from the bleed, VFD outputs spikes to stabilize it. The ultimate success criterion is velocity. Fluid at the furthest point must hold steady, never dropping below 3 feet per second. Engineers also verify that chemical purity metrics, like total organic carbon, remain within defined limits during the event. Failing this test requires immediate fixes, either recalibrating the VFD response times or redesigning the physical pipe diameters. Passing this physical simulation proves that the theoretical math of the diversity factor holds up against the brute force of hydraulic shock. A successful physical simulation extends far beyond the engineering department. Regulatory bodies like the FDA and the United States Pharmacopeia require empirical, documented proof that every system is validated under load. The exact data logged during this singular stress test becomes the foundational compliance document that legally permits the facility to manufacture active drugs. Maintaining the biological integrity of a drug batch requires a water system that reacts instantly to pressure loss across the loop. Mastering these fluid dynamics and digital feedback loops ensures that the facility's mechanical defenses remain active regardless of operator behavior. If you're an engineer or QA professional, head down to the comments and let us know about the most complex system crash or validation hurdle you've encountered in the field.